Hello and welcome everyone to another episode of Linguistics events from the Linguistic Students platform. My name is Koray, and tonight on the schedule we have Soroosh Akef. He's actually, sorry about it. He's working on computational linguistics right now. Before I give him the word, I will briefly introduce him to you. He did his bachelor's degree in English language and literature field. Then he finished his master's degree in computational linguistics. He's right now doing his linguistics PhD in Portugal, and he's actually working on language proficiency works as of now. Soroosh, thank you for being with us here tonight. You can start whenever you're ready.
Yes, it's my pleasure, and thank you for having me, and thank you all for being here. So, as you kindly introduced me, I'm a computational linguist who works at the intersection of computational linguistics and second language acquisition. And in this talk, I'm trying to convince you that despite the hype about ChatGPT and large language models, handcrafted linguistic features still matter. So, if you're familiar with computational linguistics, we have two techniques in general. We can have data-driven techniques, where we have lots of data, we feed machine learning models the data, and perhaps we can do it in an end-to-end fashion, and then we get the outputs. But then there is the rule-based approach to natural language processing, and then this requires experts to devote significant time and effort to develop rules that allow the machine to process the text. And of course, this is insufficient for complex tasks. So if you want to build something like ChatGPT, you're going to have a very hard time devising rules for it. But actually, we did have a chatbot using rule-based approaches in the 1970s called Eliza. And this chatbot was supposed to be a replacement for a therapist. So it would use the input that you would give it, and then it would try to mimic the role of a therapist. So you can see the conversation here. It's something like this. Oh, is something troubling you? So men are all alike. Oh, what is the connection, do you suppose? They're always bugging us about something or other. Can you think of a specific example? So you see, there are these cliches that the system uses, and then it tries to mimic the language that is produced by the user to try to kind of create the illusion of a conversation. But then, of course, is it all math then? If these rule-based systems cannot perform complex tasks? And some people really seem to think so. So there is this famous quote that is attributed to Frederick Jelinek that says, "Every time I fire a linguist, the performance of the speech recognizer goes up." And well, it's a really provocative quote, but it is the kind of the feeling that many computer scientists and NLP practitioners have. So in this talk, I will try to convince you that actually the role of computational linguists is different from NLP engineers, in particular with regard to the questions that computational linguists try to answer. So in order to do that, we actually try to study the language and the language development and how it happens in people. So for that, I'm going to showcase some part of the research that I've been doing as part of my PhD. And then by the end, I hope you will be convinced that, no, we still do need computational linguists who take significant time to write rules. So there used to be this assumption a while ago that the multilingual mind is something like this. So you have Portuguese in one file, English in one file, and Spanish in another file. And when you try to converse in a language, you do not kind of take any information from the other language. So the languages do not overlap in any way. Now we know that this assumption is false, and the multilingual mind looks more something like this, where we have like a web with every node being the constructions and words in all the languages you know. And then whenever you learn a new language or learn a new word or structure in a new language, what happens is that not only is that word or structure affected by all the other words or structures in your linguistic system, but it also affects the whole system and kind of moves it slightly word itself. So that's why if you're a Turkish speaker and you begin learning English, not only is your English influenced to some part by your first language, but then your first language at some times and in some aspects can be affected by your newer language. So this is nothing new. We know that cross-linguistic transfer from L1 to L2 is very well established, and we have positive transfer and negative transfer. So positive transfer is when you try to learn a language that contains similarities to the languages that you already knew. So when I moved to Portugal, and or rather when I started learning Portuguese, I had a much easier time learning Portuguese because I already knew some Spanish, and also I knew English. And because in Portuguese, we have basically words that stem from Latin and English. And in English, also, the more sophisticated words are Latin-based. So that provided me with an easier, basically, time learning Portuguese. But then there are negative transfer effects as well. So if you come from a language where you do not have articles, like I do, so I come from Iran, where in Persian we do not have articles at all. And that's why when Persian speakers produce the language, especially at lower proficiency levels, you can see that many times they struggle with using the correct article. Is it a, is it the, or should I drop the article altogether? So because of this reason, it is very interesting to know if we can identify what we call as criterial features. These are linguistic properties that can be characteristic of L2 proficiency at each CFR level. So if you are a B2 learner, we expect you to be able to produce particular structures and not be able to produce some other structures. And if we can identify these structures, that can help us automatically predict your proficiency level based on the text that you have written. And then there's, of course, the idea of L1 specific criterial features. So just as I mentioned, because in my first language, we do not have articles, it might take a longer time for a Persian speaker to be able to master articles than it would, for example, a Spanish speaker where we have articles. So if we see someone at level B2 perhaps making mistakes in the use of articles in English, we cannot quickly say that, well, this is an anomaly and this shouldn't be the case, because we should take their L1 into consideration. So this is what we need to kind of investigate. And of course, I mentioned that we know this influence exists, but what would be interesting is it significant enough? So, we know teachers are all busy people, and we don't need them worrying about another thing like the linguistic background of their learners if it's not really that significant for their language acquisition. So we need to have good evidence that, no, this is really an important factor in the development of a learner. And also, what happens if you're building a tool that provides learners with content to master the language? Imagine like Duolingo. Should we have a separate system for every L1 background, for every native language background? Or no, we can pull everyone together because it's not that big a factor. So this is an important question to address. And also, this is a relevant question for Portuguese because in recent years, Portugal has experienced an influx of migrants from diverse L1 backgrounds. And if the teachers understand that the learner comes from a particular linguistic background, then they might take certain considerations into their teaching that could benefit the learners. So the way that we propose we can quantify this linguistic transfer effect is by predicting the proficiency of the levels by training a machine learning model. And so this is a very complex task, right? You cannot write rules that quickly or efficiently predict the proficiency level of a learner based on the output they've produced. So we are using machine learning tasks, but later I will argue why we need to use machine learning tasks or machine learning models that allow us to basically see exactly how the model is making its predictions. And so the model that we are going to train is an automatic proficiency assessment model, where it tries to predict the CEFR level of a learner, like the proficiency level of a learner, based on the text that they have produced. And the way we do it is to divide the data that we have into sets. And just like how a human might learn, we show the computer, we show the model examples, and then we tell it the proficiency level that that learner was at. And then the model learns patterns in the data, and then we test it by showing it the one part that we do not give it the answers for, and then we see how well it performs, right? But then computers need numbers, right? They do not process text. Even ChatGPT or any other natural language processing system, what goes on behind the scenes is lots of number crunching. And this is where computational linguists enter the scene, because how we represent text as numbers is really important for what you're trying to do. So imagine if you're, for example, we have a text like this. It is beyond comprehension how any company could hold itself in such low regard as to produce a product so dreadful. So I assume this is a review on a website. How do you represent this text as numbers? Well, it depends on your task. If you have a sentiment analysis task, perhaps what you would be interested in are the words that convey a feeling that the person who wrote this review had. So, for example, dreadful. Like you could perhaps take a very simplistic approach by just counting the negative words and positive words and then representing the text in terms of those numbers. Or you could take a more sophisticated approach. You could have semantic word embeddings, where the model learns the semantic information of each token based on the words that it appears next to them. And then it can predict whether the sentiment in this sentence is good or bad. But then what happens if you want to know the proficiency level of the learner who produced this text? Then that kind of information would not be as informative for you. So you need to represent this text as numbers in a way that is informative for the task that you are trying to do. And this is where we ask, okay, so what is your quest? Our quest is to predict proficiency. And luckily, for predicting proficiency, we have this operationalization of proficiency, where we say proficiency has three dimensions: complexity, accuracy, and fluency. Where complexity is the ability to produce more elaborate structures and vocabulary. Accuracy is the degree of conformity to a particular norm. Now, what is that norm? That is a matter of debate itself. And fluency is the spontaneity and the rapidity with which you can produce the language. So in order to be a proficient learner, you need to produce complex language accurately and fluently. In everyday language, sometimes people use fluent in place of proficient, but we know that fluency is really only one aspect of proficiency. So the questions that we're trying to answer are really simple. We want to see if an L1 specific proficiency assessment system generalizes better to unseen samples compared to a general system that has more data. So, because generally we assume that more data means better performance. But if the data is not of high quality, then more data doesn't necessarily mean better performance. So if being L1 specific makes the data of higher quality, then we should expect to see a smaller model trained on L1 specific data to perform better than a larger general model. And we also want to observe if we find patterns between texts that were produced by learners that were at the same level of proficiency, but came from different L1 backgrounds. And in particular, we're going to focus on complexity and accuracy features. So we're going to represent texts in terms of numbers based on their complexity and accuracy. And we'll see how we do that. So the corpus that we have is this couplet 2 corpus, which is a Portuguese learner corpus. So we have a collection of texts produced by learners. You can see around 1,600 texts. And that makes up around 270,000 tokens. And we have learners from 15 different native languages that span across 5 proficiency levels. So we don't have data for C2, but that's fine because the majority of learners are at levels A1 to C1 anyway. And at level C2, you're probably not looking for any language resources to make yourself more proficient. And these were all texts that were collected as part of exams of Portuguese classes at the Institute of Teaching Portuguese as a Foreign Language at the University of Lisbon. So when we see the distribution of the texts across different L1s, we can see that Chinese, Spanish, and Italian make up the most number of texts. And this is actually very fortuitous for us because Chinese, Spanish, and Italian, or at least Chinese, is a different language typologically from Spanish and Italian, which are both Romance languages. So because of this factor, then we can perhaps see if language typology has any effect in L1 transfer. So then, of course, we need to be cognizant of the fact that at level C1, we have some sort of imbalance, especially in Spanish and Italian, and also at level A1 in Chinese and Spanish. And data imbalance is always a nuisance in statistical and machine learning tasks, but that's something that we need to take into consideration. So we said we want to represent texts in terms of their complexity features, and the way we do that is by using the system that uses rule-based natural language processing. So basically using dependency information, part of speech information, and other pre-processing information, we can identify kind of parts of speech or parts of the language that can allow us to calculate these complexity features that can allow us to predict proficiency. And you can see we can extract a broad range of complexity features. So we have 489 features that span across like syntactic complexity, lexical complexity, morphological complexity, and discourse complexity. And syntactic complexity is basically how complex is the syntax, like prepositional phrases per sentence is one feature. Or lexical features can be just as simple as word frequency, or it can be type to token ratio, or it can also be like measures that are derived from psycholinguistic research, like imageability, age of acquisition. So these are all features that we can use to train our model. We can also have morphological features, especially for languages that are highly inflectional, like Turkish or German. Morphological features are expected to play a bigger role in predicting proficiency. And we also have discourse features like connectives, coordinators, things like that. Then we have accuracy features that were based on error annotations in the learner corpus. So in the learner corpus, experts went through each text and they annotated every text for the mistakes that the learners had made. So these errors can be grammatical, like verb tense error, wrong structure. They can be lexical errors, like using non-existent words or using the wrong word. Or they can even be orthographical errors, like it's very strict, like grapheme deletion or word boundary split. And then we also calculated another accuracy feature that contained the total number of all errors. So just a coarse-grained feature to see if that is also a factor. And then we also, of course, normalized these measures to make sure that they are not length dependent. And this is very important. So the complexity features that I mentioned, we also use length independence measures because so in previous research, we have shown actually that when we use these length dependent features, so they're like number of words, number of verbs, then that is really a proxy for the length of the text. And what we're saying is that the longer the text, the higher the proficiency, which is not a valid indicator of proficiency. So I mentioned that we need to use machine learning models that are interpretable, and this is where we get to them. So traditionally, it used to be the case that we had this sort of trade-off between accuracy and interpretability, according to which we had models that were interpretable, like these glass box models, but then they could not really capture complex relationships. And then we had these black box models that were more powerful, but then you could not really interpret their findings. Of course, this is really a spectrum. So like models like random forest, sure, you can calculate feature importance, but then that is still limited because you cannot really see exactly how it's using that feature to make its predictions. But And thankfully, due to recent algorithmic advances, we now have the best of both worlds. So we have these what are called explainable boosting machines that are machine learning models based on statistical generalized additive models. And they are both highly accurate and fully interpretable. So they allow us to kind of plot these sorts of diagrams that show exactly how each feature contributed to predicting the proficiency of the text. And these models are used in high-risk applications like healthcare or finance, because, well, let's face it, imagine you are applying for a loan and then your loan request is rejected, you don't want them to say, well, sorry, we rejected your request because we asked ChatGPT and it said we can't give you a loan, right? So you want them to at least have a good reason. And then these models are really good to extract knowledge from the data because of this exact interpretability. So this is the procedure that we took. So we took each L1 background and we divided the data into 5 parts. Then we trained the model on 4 parts and tested it on the remaining 1 part. Then we took those 4 parts and added them to the text from all the other L1s. So we made this huge general data set, but then tested it on that exact same part that we tested the initial model on. And then we repeated this process 5 times by alternating the test set. This is called k-fold cross-validation. It's a very common technique in machine learning to make sure that basically the results we get is not an effect of chance, right? This minimizes the effect of chance. And then we average the results and then calculate the accuracy of the model. So let's see how the models perform. So you can see in every L1, the L1 specific model actually outperforms the general model, even though we had a lot more data in the general model. But we thought, okay, that's all well and good. What happens if we train an L1 specific model on the full L1 data set and then test it on the data of the other L1s? And then here is where things get interesting. So again, we can see that for each L1, the model performed better when it was tested on its own data. But then you can see that for L1 Spanish and L1 Italian, the performance of the model on L1 Italian, for example, for L1 Spanish, is better than L1 Chinese. So this could be a factor of linguistic typology, because L1 Spanish and L1 Italian are closer to each other. This could be a tentative evidence that, you know, linguistic typology has a role here. And the same thing can be said for L1 Italian. You can see when L1 Italian was tested on L1 Spanish, it performed better than L1 Chinese. So we thought, okay, we said that our model is interpretable, so let's see which features it kind of leveraged to make predictions. So when we calculated the top 20 most important features for L1 Chinese, we can see that, well, we have a range of different features. We have accuracy features, we have lexical features, morphological features. But the most important feature for the model was token accuracy rate. Remember, this was the coarse-grained, like, like counting all the errors in the text and then making a prediction about the proficiency of a learner based on that, which is kind of weird, because what is it saying? Is it saying that you can count the errors in the text and kind of assume that the learner is at a certain level of proficiency according to that? So the more errors you make, does it mean that the less proficient you are? And we thought, okay, let's look into how the model works. And then here you can see that actually at level A1, so actually before, let me tell you how we should interpret this. So on the x-axis, we have the normalized or rather standardized feature. So here is 0. This is the mean of this feature, token accuracy rate. And then this is the standard deviation from the mean. So here, the more we move to the right, the more accurate it is. And the more we move to the left, the less accurate. And here on the y-axis, we have the logit score. So this is a transformation of probability. So the higher it is, the more likely it is at that level. And the lower it is, the less likely it is. So you can see at level A1, learners are actually a lot less likely to make errors. So this is because at level A1, you don't really have much of an opportunity to make errors, right? I mean, most of the structures and phrases that you're dealing with are very routine and learners quickly master them, and you don't expect many errors at level A1. But at level A2, you can suddenly see this drop because suddenly students are hit in the face with all these new structures. And the very interesting finding was that actually C1 learners are more likely to make mistakes, because possibly they are thinking that, okay, we are more advanced, we need to show off our vocabulary and the structures that we've learned, and they are becoming, let's say, too liberal with the language and are taking liberties that they should not be taking. And this could be a result of that. So you can see how using these glass box models and handcrafted features, we can extract this sort of knowledge from the data. Then when we looked at the top 20 most important features for the L1 Spanish model, then you can see here, it seems like lexical features play a bigger role. So we have imageability, that is how quickly a word conjures an image in your mind. So for example, chair is very imageable, but ethics is less imageable. Concreteness is also highly correlated with imageability. And then when we plot how the model uses imageability for predicting proficiency, we can see, okay, this is exactly how we expect it to be. So A1 learners are using more imageable words, more concrete words, and C1 and B2 learners are using less imageable words. So this is a sensible way to predict proficiency. Excuse me. And then there's something interesting also happening. So here we're seeing that the model is actually using gender and number error rates. Excuse me. So this is actually very interesting, because for the L1 Chinese model, we could also see that this feature was used by the model. But then Chinese and Spanish are very different languages in terms of their gender and number, right? So we thought it would be interesting if we see how each of these models are taking advantage of this feature. So when we plot this visualization, we can see that for L1 Chinese, by the way, this plot is reversed. So here we have the error rate, not the accuracy rate. So we can see for L1 Chinese, again, A1 learners are making fewer errors, and B1 learners are actually making more errors. But when we look at L1 Spanish, something interesting is happening. We can see C1 learners and A1 learners both are committing very few errors, but it's actually B1 and B2 learners who are producing more mistakes. And what is happening here is false cognates. So these are words that have the same cognate in both languages, but have, or rather they are cognates in both languages. They have the same root in Latin, but they have different genders. And at levels B1 and B2, learners are using their knowledge from Spanish to use these genders. But then at level C1, they realize what's going on and they learn this difference. So this is a very interesting way to look into how L1 transfer characterizes proficiency. So ultimately, when we looked at the top 20 most important features across all three L1s, we see that only 3 features appear among the top 20 features for all 3 models. And these are all lexical features. So we have word frequency, in particular, standard deviation of word frequency, which is a measure of lexical diversity. And then we had concreteness for lexical words and all words. So what this is telling us is basically that if you are training a model that doesn't take L1 into effect, then you could perhaps use frequency and concreteness. Otherwise, then the models are actually going to be very dependent on the L1. And training an L1 specific model with much fewer data, 5 to 10 times fewer data, can actually outperform a larger model that doesn't take L1 into consideration. And then, so here, using this experiment, we showed that how we can combine linguistic features with transparent glass box models to ensure learners and educators that the features that the model is using are valid and fair. Because think about it. If we hadn't looked at these features and we had used an end-to-end model or a black box model, then the model would have still used features like total accuracy rate And then it would happily tell you that, okay, I'm getting this accuracy, and you would happily declare that as a win. But what would be happening is that the model is using a feature that is not valid, because in real life, you would be penalizing learners for not making mistakes, because you're saying that, oh, if you're not making mistakes, then you're at level A1, because A1 learners don't make mistakes, which is not fair to the learners. So this way, we can make sure that our models are valid and fair, and we can also extract knowledge from the data. So I hope now you're convinced that computational linguists are still valid. We're not going away, especially because we address questions that are different from NLP experts. I thank you for your attention, and I look forward to your comments. And I thank the organizers for inviting me.
Soroosh, thank you for your presentation. You really emphasized why taking L1 into consideration matters. Like, as you said, like we as computational linguists, we as linguists in general, take a different approach on what we do from the different fields. So it's really important, really. Yeah, we being on the field is really important. Thank you for emphasizing on that, yes.
Absolutely. It's about, it's really comparing apples and oranges. So I'm not discounting the role of NLP engineers and artificial intelligence, or all these end-to-end models. They are crucially important, and they are adding a lot of benefit. But what we are doing is kind of different. We're asking different questions, and we're going in a slightly different direction if we are using, even if we are using the same tools and techniques, let's say. Yeah.
Well, that's completely correct, as you said, as I said before. If you want, we can move on to the Q&A session. Like, we can answer the questions if you want to.
Absolutely, absolutely.
Okay. If you have any questions from listeners, you can ask it in the chat box, or you can raise your hand to take a word. Anything. People are thanking you for the presentation, Soroosh, in the chat box.
Thank you.
Ferlin saying that. I would like to thank you very much, both on behalf of myself and the platform, for accepting our invitation and sharing your time and knowledge with us today. It was a very informative and enjoyable presentation. Let's keep in touch in the future.
Absolutely. Absolutely.
Yes, I also agree with Ferlin. Thank you. So Meryem Nasiri has a question. I hope I'm not butchering it, the presentation of her name. How EBM handles data imbalances.
Right. So basically, data imbalance is always an issue there. And actually, so I actually have a slide here, so we can see actually how the model is making its predictions. So this is the confusion matrix, where we see where the model is making its mistakes. And for the L1 Chinese, so we can see it's mostly, it's performing as you would expect it, more or less. But then here for L1 Spanish, because we had fewer data at level C1, the model is also performing worse. So, that is an issue that we always face, and ideally, you would want to have as much data or as much balanced data as you can. Perhaps, so based on this, we can say that perhaps we can make fewer assumptions, or we can make less certain conclusions about level C1 here. That is always an issue. So if you can have balanced data, that would be ideal. Now, about exactly how EBM handles it, off the top of my head, I can't exactly tell you the inner workings, but you can see that it is not performing well when the data is imbalanced. Or here we have one Italian. Yeah, that is still a problem here.
Yeah, in Italian, it shows that it has really problems there. As you mentioned, it actually, in general, algorithms work better when they have more balanced data towards its working conditions. So in your second question, she asked, you said EBM shows specific contributions of each feature. How does it do compared to the feature importance in random forests in terms of assigning numerical values to each contribution?
Right. So basically, random forest is really driven by randomness in a sense. So you cannot make inference based on the most important features you get in random forest for the most part. But these EBMs are really exact. So I mean, they've kind of flown under the radar. Not many people have heard of them, but they are really powerful. But basically, what they are doing is they're using like common techniques in machine learning, like bagging and boosting, but in a way that makes them exact. Now, again, like if you're interested in the exact inner workings, there are like lots of great videos and tutorials that explain exactly how they work. So they kind of iterate over every feature for every fold, and then they kind of average the performance over over every run. But then, yeah, I would say the advantage that EBMs have over random forest is that they are exact in their output of the most important features. But random forests are driven by lots of randomness there, and you can make less conclusions or less strong conclusions about them.
Thank you for your answer. So I'm checking if we have any other questions. There are people thanking you in the chat box, but I believe that's all questions that we have tonight. So we have a question. I had a question about how the relevant data was gathered. However, I was a little late, so if it has been talked about, you can skip it.
Well, no, I mean, that would be all right. So basically, let me go back to the slide where I mentioned the corpus. So the corpus was gathered by texts that were produced by learners that produced them in class as part of exams of Portuguese as a second language. So yeah, that's then. So I was not involved in creating the corpus. I'm just using the corpus, but this is how the corpus was created, basically by collecting text and then annotating them for errors and also for other linguistic information like part of speech.
Great, thank you for your answer. I believe that's much appreciated. Thank you. Answers Satyu Yilmaz, the person who asked the question. And I believe that's it. We don't have any questions left. Soroosh, thank you for being with us here tonight. It was a great presentation. Thank you for your all of your presentation and all of your details and stuff. It was a really detailed group of information you provided us here tonight. So thank you for it.
Thank you very much. Thank you for having me, and thank you for organizing these events. And it was a real pleasure.
Thank you. We can end it now. And I would like to see you in the future episodes as well, when you finish the project, hopefully.
Absolutely.
Of course. By the way, we are actually recording it. I asked you beforehand, but I didn't actually ask you if you're okay with us uploading it to YouTube.
Of course, absolutely. That's absolutely
okay. Thank you then. Thank you.
Thank you.
Have a great night, everyone. Thank you for being here. And Soroosh, thank you again for participating, for presenting us with your presentation tonight. Good night, everyone.
Thank you. Good night, everyone.